Hello, ladies and gentlemen. We're going to do 4.3 today. We're going to kind of breeze through Riemann sums, and then we'll talk about definite integrals. We're going to use our Riemann sums to calculate the area under a curve. We're going to evaluate a definite integral using limits and show you how the two are equal, and then we will evaluate a definite integral. So let's talk about our Riemann sums first. Okay. And remember that these are used to estimate, because we're not doing a definite integral, the area under a curve. All right, so if you'll think about it, a left Riemann sum, I'm spelling the word wrong, I think. So, and I'm going to draw a picture because I think it's easier. If I have a curve and I have some boundaries for that curve, and I have 1, 2, 3, and then maybe 4, and I draw my little rectangles, so I'll draw my little rectangles, right? And then this rectangle, and then this rectangle, and then we'll say, we'll just pretend that there's one in there. Okay, so those are my rectangles, alrighty? So the left Riemann sum is going to utilize the left hand side of the rectangle. Okay, so this might be the left of rectangle number 1. This is rectangle 2, 3, and 4. Then this would be the left, this would be the left. So remember, what I'm doing as I use a Riemann sum is I'm summing the area of the rectangles. Okay, so I'm summing the different areas, and I can use, I have to have a height, and I have to have a width. Well, the height is always going to be the function evaluated at either the left, the right, or the middle. Okay, and so basically when I do a Riemann sum, I'm calculating the area of these 4 different rectangles, or however many there are, and I am summing, and I'm either using the left-hand side as the height, I might be using the right-hand side as the height, or I could use the midpoint of that space as the height, and then I would multiply by delta x. The other thing that's important to remember is that delta x does not have to be consistent. So it kind of depends on the nature of the problem, right? So if they tell you that they want all of the delta x's to be the same, then you would do b minus a, your endpoints, and you would divide it by the number of subintervals. But if they just give you a curve, so here's my curve, and maybe they have a fat rectangle, and then I have a skinny rectangle, and then maybe I have another one, and then another one, and then another one, it is irrelevant if delta x is different, okay? So it doesn't matter if delta x is fat or if maybe delta x number 2 is skinny. It really doesn't matter. You have to pay attention to the problem. What becomes more important is noticing what part of the rectangle I want to use. Do I want to use the left-hand side as the height? And remember, I would evaluate the function at whatever that left x value is. Or do I want to use the right-hand side of the rectangle? And again, I would find the height by evaluating the function at the right-hand x. Or do I want to use the midpoint? Okay, and they usually tell you what they want you to do. All right, so just to finish this, the right Riemann sum is going to use the right-hand side of the rectangle. And then I don't know that I necessarily need to write out the middle, but the midpoint Riemann sum is going to obviously use the midpoint. And again, these are the values. So if I evaluated the function at midpoint 1 and then I multiplied it by delta x 1, and then I multiplied, or I found, sorry, the y value of the second midpoint, and I multiplied that by that delta x, right? If all the delta x's are the same, then I can factor those out, which makes my math a little bit easier. And then plus dot, 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 and then I'm summing, and I'm summing from A to B. All right, so that's basically what the Riemann sum is. And I don't know that I necessarily need to write out any formulas for you to remember, because I just have to manage which particular side of the rectangles that I am trying to sum. You could also, and we haven't talked about it, I don't think it's in this section, but if you wanted to do a trapezoid sum, right? So if I wanted to estimate the area under a curve, maybe using my trapezoids, the process is always going to be the same, because here would be my trapezoid, right? And I have B1, B2, and then here is the height, except you can't see it. There would be the height in between the two, and I sum up all of my trapezoids, ta-da, done. Okay, so it really, once you understand this concept that an integral is a summation of all of the individual components, then that means that calculating the area under the curve using either rectangles or trapezoids is really quite simple. All right, so in this section, the next thing that they want you to understand is that if I write the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x sub I, okay, and so notice that's calculating the area under the curve by summing all of the heights and the widths of the rectangles. This is the same thing as writing an integral from a to b of f of x dx. So both of those things do the same thing. This is obviously significantly harder, and in my opinion, this is a lot easier. But it gives us different ways to approach the same calculating the area under the curve. All right, so we're going to do an example where we don't use a definite integral, which is this. We're going to do this process. So we're going to start with the area is equal to the definite integral from 2 minus x squared dx, and I want to convert this to the limit form, and then I want to calculate the area using the limit form, and I'm calculating the area under the curve. Well, if I know that delta x is going to equal 2 minus 0 over n, then that's going to be 2 over n, because I don't know how many sub-intervals. And I'm going to do the left-hand side, so I'm going to say x sub I is going to equal my left-hand piece plus delta x times I, right? So that's going to be the 0 plus delta x, which is 2 over n times I. Alrighty, so this is my x sub I. So now I know that the integral from 0 to 2 of 2 minus x squared dx is going to equal the limit as n approaches infinity. And let's talk about what that means. As the number of rectangles approaches infinity, that's going to give me the area under the curve. All right, and I'm going to have my function, remember, where'd it go? My function, write it right here, is 2 minus x squared. So I need my function evaluated, so I'm going to do 2 minus x sub I, quantity squared, that's the function evaluated at x sub I, and then times, oops, I forgot the summation from I equals 1 to n, and then multiplied by my delta x, and my delta x was 2 over n, okay? All right, oh, I didn't do this very well. I'm going to do that. There we go. Okay, so I have the sum from I equals 1 to n of 2 minus x sub I, and then this is my delta x. And so if I just finish this, this is the limit as n approaches infinity of the sum from I equals 1 to n, and my x sub I is 2i over n, so it's going to be 2 minus 2i over n, quantity squared, and then times my delta x, which is 2 over n. Well, remember in these problems that the 2 over n is the variable, so right at the beginning I'm going to pull it out front. So I'm going to have the limit as n approaches infinity, and I'm going to pull that 2 over n out front times the sum from I equals 1 to n, and I'm going to have 2 minus 4i squared over n squared, okay? And then what I'm going to do, instead of putting these two things together, I'm going to manage this, and I'm going to ignore my phone, sorry. And it's on my computer too. How do I make it go away? There we go. All right, whew, that's exciting. So the limit as n approaches infinity of 2 over n, and then if I manage, well, remember that the 2 is going to have 2 to the n, right? And then I'm going to have minus 4 over n squared, and then I'm going to have I squared, which is n times n plus 1 times 2n plus 1 over 6, and then that is what I have to manage the limit of. Alrighty? If I simplify this a little bit, and what I mean by simplify, I think it would be prudent to distribute at this point. So this is going to become the limit as n approaches infinity of 4n over n, and then I'm going to have minus 8 over n cubed, and then I'm going to have I'm going to go ahead and distribute this n squared plus n, and then I have 2n plus 1 over 6. It's getting a little bit better, okay? Guess you can't see it, not bad, okay? So then, at this point, notice that my n's cancel, okay? So this is going to be the limit as n approaches infinity of 4, and I'm going to keep my 8 over n cubed, and we'll leave that there. And then if I distribute this mess, oh, and I have my 6 in there. I'm going to stick him over there. If I distribute these two guys, I get 2n cubed plus 3n squared plus n. Yes, I skipped a step. My bad. I did this before I got there to make sure that I didn't make mistakes. 2 goes into this 4, 2 goes into this 3. So now I have the limit as n approaches infinity of 4 minus 4 thirds n cubed, and I'm going to distribute this times each of these terms. Okay, so I guess I could have rewritten it, but I'm just going to do it now. Okay, and if I distribute, this is going to be the limit, which I guess I could have done, but oh well. Here's the 4 minus 8n cubed over 3n cubed, right? And then I have plus minus 12n squared over 3n cubed, and minus 4n over n cubed. All right, that's a lot of mess. Well, notice that the n cubes cancel. This is going to go to 0, and this is going to go to 0 because I've divided by a higher degree. I'm approaching infinity. So then all I have left is 4 minus 8 thirds. Woohoo! That's actually kind of nice. And then if I simplify that math, 12 minus 8 is 4, so my limit is 4 thirds. So, I'm going to go back and write it this way. The integral from 0 to 2 of 2 minus x squared dx is 4 thirds. Yes, there are simpler ways to get there, but it is important to understand that if I do my limit process, I will get the same answer as if I evaluated the integral. Alrighty, so a couple things that I want you to remember from our Calc 1, okay, and it's when we start talking about calculating the area under a curve. So there are quite a few different ways that you can actually calculate the area under a curve. One is you could use your geometry formulas, and it can look a lot of different ways, right? I could have something that looks like this, and this is a -2, and this is a +2, and I could calculate the area under the curve by calculating half of the area of a circle. And we know how to use our geometry formulas, and that would give me a nice approximation of my area. The next method that I could use is I could do my summation formulas. Okay, so I could do my summation formulas. They're not my favorite, but it does greatly illustrate what an actual integral does, and this is actually our precursor to our definite integrals. Alrighty. The next way, obviously, then is I could use a definite integral. Definite integral. And if I use the example that I had there, I could do the integral from a negative 2 to 2 of f of x dx. Alrighty. And then I could also use my Riemann sums. And my Riemann sums really are kind of the same thing as doing the summation formulas. It just depends on how the question is asked. And oftentimes they'll say find a left Riemann sum. And so if I have my handy dandy curve and I have some subintervals in there, and remember that delta x can be b minus a over n if they want you to have equally divided rectangles. If I use this one, and this one, that's going to give me my left-hand sum. If I did, this is going to get tricky, this one, and this one, that would give me my right-hand sums. And then I could do this one, this one, this one, and that could give me my midpoint. And remember, what I'm doing when I do a Riemann sum is I'm summing the area of the rectangles. So I'll write area of my rectangles. And those are the sum from A to B of the heights, and I'm going to call it x sub I, and then times whatever the delta x is. The other thing that's really nice to remember is delta x does not have to be the same for each rectangle. As long as I calculate the individual delta x's, I'm good to go. All right, so now we're just going to get some information about properties of our definite integrals. All right, so I can integrate from a to b of f of x dx, and I could get 0, right? Oh, sorry, my bad. That's got to be wrong. It's got to be a to a. Okay, that's just creepy. I don't know why we do that, but there you go. All right, I could integrate from a to b of f of x dx, and it would be the same thing as integrating as a negative b to a of f of x dx. Okay, so if I integrated the opposite direction and took the negative, then I would get the same area under the curve. If I do the integral of a to b f of x dx, I could split it up, which I'm going to show you a cool example of in a minute, a to c of f of x dx, and then I could integrate from c to a of f of x dx. And remember, sometimes this is especially helpful if I have changes in my shape, then I can manage and just, oops, that's a b, integrate in pieces and then add all of pieces together. Alrighty? Or I could go the opposite direction. I could say the integral from a to b of f of x dx plus the integral from b to c of f of x dx is the same thing as integrating from a to c of f of x dx. So there's so many different ways that you can do your math. All right? If I have an integral a to b of a constant times f of x dx, remember, I can yank that little constant out front, a to b, and then I can have my f of x dx on the inside. The last property that we have is if I have maybe, and remember you really need to use your parentheses because you get dinged for your notation. If I have two functions added together, dx, and I'm integrating from a to b, then I can split that up to be the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So sometimes I can split things up and that works very nicely. All right, so we want to talk about an absolute value function. So let's say I have it is an example, but we're really just going to kind of talk through it. I have an integral from a negative 1 to 1 of the absolute value of x dx. Okay? So if I think about the graph of the absolute value, it looks like this, right? And let's say this is a negative 1, so that means that's 1, right? And then if I have a positive 1, then that's 1 also. So it's interesting because I really I can calculate the area of the curve under this piece, and I can calculate the area under the curve of this piece, but an absolute value, really is a piecewise, and so it's a negative x, and then it would have for x, and then it would have a condition, and then it is a positive slope, and then x would have a condition. So I can do this same basic idea with my integral. So I could split my integral up, and I could go from a negative 1 to 0 of f of x dx, okay? And I'm going to change this in just a minute, and I would add it to the integral from 0 to 1 of f of x dx. But because I have an absolute value, and because this equation is actually different than this one, what I should say is this is the integral from a negative 1 to 0 of a negative x dx plus the integral from 0 to 1 of x dx, right? Because this side is the y equals a negative x, and this side is y is equal to x. And so I can manage my absolute value by splitting it up into a piecewise and integrating in sections. Alrighty, that's it for today. I will see you tomorrow.